Okay, let's get started. So, this is a little bit loud. Okay, let's get started. So we are going to try to wrap up today. So we have finished the network layer last week, right? And I think that I ended by talking about Steiner trees and minimum spanning tree, right? And there was a document that I had brought up, and there were some questions about it, so I thought maybe can address some questions about it. Yeah, so if you recall, we were talking about the broadcast problem, the broadcast and multicast problem. And in broadcast and multicast, you can have multiple senders and multiple destinations. This is in contrast to unicast, where there's one sender and one destination, right? And we essentially saw that the solution to the broadcast or multicast problem is to form a spanning tree. And if you have a single sender, you can do a spanning tree rooted at the sender. This is the same strategy that we use for link state routing, where we did Dijkstra's algorithm. Right, now, maybe somebody can tell me, why is it that in link state routing, we were able to use Dijkstra's algorithm, which is a spanning tree, shortest spanning tree rooted at a certain node? Why is it that in link state routing, that is the appropriate thing to do? Yeah? Yeah. Okay, but why should we do so where is this routing done? Yeah, thank you for that. Where's the routing done? Where's the algorithm executed? Is it, so we call it centralized, right? So is it done in a central place? So yeah, that's right. So this is appropriate because every node in the network or every router is computing this shortest path route, right? And since it's computing it, it's going to do it from the references itself, which is why a shortest path from itself is the appropriate thing to do. And it makes sense in broadcast, if you have a single transmitter, then you would do the same thing, right? And then when you have multiple senders and multiple destinations, then maybe you want to do something different, and that's where the shared spanning tree comes from. And we had two concepts: the minimum spanning tree, which is amongst all spanning trees, which is the one with minimum cost. And then there was the idea of Steiner tree, which is also a shared tree, but it can include nodes that are not destinations. And the example I gave was this. So this is a road traffic network. And we said, let's say you have 5 nodes. It could be 5 nodes, cities, routers. It doesn't matter. And what you want to do, I think the problem I gave is, let's say you want to, for the moment you can ignore, let's ignore these things for now. Oh, I can't really. It's okay. For the moment, ignore everything, and let's say you just have the 5 nodes, the 5 cities, the 5 routers, and you want to build links or you want to build roads. And you ask the question, what's the minimum amount of material that you have to use? Let's say it costs you, $100,000 per kilometer, right? And I tell you, this is all in kilometers. And you want to spend the least amount of money to build your road. So how would you do it? Well, the minimum spanning tree is shown in green. Okay? This is the sort of, if you just said, I'm going to build roads between cities or connect up routers, then it would cost you about 52. So this is in yeah, whatever units, don't worry, let's assume this is in units, so it would cost you 52 units, right? But if you're willing to, the purple is the Steiner tree. If you're willing to lay down an intermediate intersection, the purple point, then you can reduce the cost to 50. So this is the difference between Steiner tree and minimum spanning tree. That purple point is not an end destination. So it could be a router that's not an end destination. But if you use it, you can reduce the overall cost of the spanning tree. Okay, and it turns out that the Steiner tree is an NP hard problem. The minimum spanning tree is, it's very similar to Dijkstra's, like to finding a shortest path spanning tree, right? You could almost see, right? It's similar. So for that reason, the complexity is the same as that, which is approximately order of n squared, or if you do it efficiently, n log n. It still scales with n, right? But the minimum spanning tree, the Steiner tree is an NP hard problem. Okay, so I reviewed this because some people came and asked me questions about it. So I thought I'd review with everyone. Are there any questions? Are we good? So with this, we wrap up the network layer. Actually, not really, because I have a couple of things that we're going to review. Okay. See, if you look in the lecture notes, you'll see there's a supplemental handout for TCP and for routing. So that's the goal today. These two. There's also, so we've already done the minimum spanning tree and Steiner tree, right? This handout here is a write-up for you. It clarifies very explicitly the definitions of these of MST and Steiner tree. Then I want to talk about some networking in the real world. Then if we have time, we'll wrap up the why questions. Okay. This handout here, this Word file that I just showed is here. Okay, that I drew in class last week. Okay, so let us talk about the throughput. About TCP throughput. Okay, so as I said, so we're done with transport and network layer. Let's just go, just do a little bit of review and maybe some new stuff as well. Can you guys remind me? We have not done this, right? Did we talk about TCP throughput and resource allocation? Yes or no? No, right? Okay, so that's fine. Okay, so. I will use, if I can find, okay, here we go. Okay, so TCP was the protocol for end-to-end reliability used at the transport layer. And we've already discussed this. I think I asked you, right, a few times to estimate the throughput. Let's make that explicit. So let's say we have, so if you remember, TCP uses this idea of congestion window to control the rate at which it pumps data into the network, right? And then it's probing, right? It's taking that congestion window and it's adjusting it. It's increasing it when packets are getting through, and it decreases it when bad things happen. The bad things, okay, let's see, remember, what are the two signs of congestion, or the two signs that bad things are happening? Yeah, Benita, you? Okay, triple duplicate acknowledgements, and then what's the second one? Timeout, okay? So, right, so TCP is adjusting its congestion window in response to what's happening in the network. All right, so we're going to assume a congestion window of W segments. Okay, for this analysis, for throughput, I'm going to assume no slow start. The reason is TCP spends most of its time in AIMD. Okay, yes, there are many slow starts, but if you look at these traces, there's very few instances comparatively, relative to the AIMD phase. All right, so we're going to assume no slow start, round trip time of RTT, segment size of MSS, bytes per segment. We asked what is the average throughput of TCP, right? And in the same way, if you remember, TCP uses a sliding window. So in the same way that you can compute the throughput of stop and wait, which was 1 over RTT, so actually that 1 over RTT is actually the sending rate, right, of stop and wait. It's the rate at which the sender sends packets, right? It waits RTT seconds for an acknowledgement. So, but that's a sending rate. We can do the same thing for TCP. TCP uses a sliding window of size W, let's say. So that's W segments. So the sending rate is W over RTT. I think that's all I'm saying here. Okay? So the sending rate is W over RTT segments per second. And if you want to convert that to bytes per second, since we have MSS bytes per segment, it's WMSS by RTT. So this is the sending rate. Now, clearly, the receiving rate, so the throughput is the receiving rate. And, well, clearly the throughput cannot be greater than the sending rate. Right? So the throughput is upper bounded by the sending rate. So that's our first order approximation of the throughput of TCP. Okay? Essentially W by RTT, or in bytes per second. Okay? We can get a slightly more refined estimate if we take into account the dynamic nature of TCP. Right? Assume that, for example, that the dynamic, that the throughput is changing. We're in AIMD phase, and in AIMD we go up and then we go down. And now assume that at a congestion window of W, you get a triple duplicate ACK. You're going to cut the congestion window in half, let's say. So now we get this sawtooth wave. So this is like our second order model for the rate, this sawtooth wave that's shown here. Okay? And it's going to go between W and 1/2 W. Again, it's an approximation. It's to try to capture some of the dynamics. Well, but since this is linear, this is very simple, right? It's just the average of the throughput at the minimum and maximum congestion window. So you end up being 3/4 W by RTT. Okay, that's kind of the second order approximation. But you can see it's essentially the same. It's capturing the same dynamics, right? So virtually any kind of approximation, let's say call it, there's a class of first order approximations for which the throughput scales linearly with W and inversely proportional to RTT. And there's a whole class of those. If you want to really take into account the, let's say, second order dynamics of TCP, you need to take into account losses, right? Because there's losses in the channel and retransmissions. That would be the second order. Then you take into account like the loss rate and so on. In this class, we're not going to do that. For us, it's enough to capture W by RTT. Okay, so just be, if you need to make an assumption about the throughput, just state your assumption, okay, and justify why it makes sense. All right, so this is essentially our model for the performance, meaning the throughput of TCP. And we can use this, so like, this is just an example. So I call it TCP over fast links, right? So this example is to highlight that sometimes if you have a very fast internet connection, that your performance is not only determined by that connection, it's also determined by how your client is operating, meaning the congestion window size, right? So here's an example of, I have a very fast connection. I have a gigabit per second, or in bytes per second, 1.25 gigabytes per second. It's a very fast connection. And you might think, oh, with this fast connection, I'll always have very fast data access. Well, actually, this example will show you that you need to have a very large congestion window size for that to happen. Right, and so we're going to do that. Okay, so what is so here, link capacity is gigabit per second, MSS is 1500 bytes per second, RTT is 100 milliseconds. Okay? And we're going to just say, okay, what's the required window size? Well, I'm going to assume my throughput is the sending rate, so WMSS by RTT. And then I can just kind of manipulate this, solve for W, and get the units right. All right? It's important you get the units right. So once you do that, right, that's why if you notice I converted things up here, to this was bits, this was bytes, this was in milliseconds. To make sure that all the computations work out right and cancel properly, you have to get everything to the same units. Okay? And then you will get that your congestion window actually has to be 83,000 segments. Right? Now, so with a 10 gigabit per second connection, for me to actually use that link capacity, this is my minimum window size. So can somebody comment on whether I'll actually achieve the link capacity or not? Like, can I not? What do you think? You're shaking your head. No, but... No, I'm saying, let's say you have 10 gigabit bit per second connection. You're rich, and you can buy it. Okay, so another question is, can you actually utilize that link? If yes, why? If no, why? Why? Okay, that's a good observation, but why? Why do you think the window size cannot be so large? Yeah, you're on the right track. So, yeah, correct. So, I'm waiting to hear something. You're on the right track. So, congestion window is not the only thing that sets the window size. This is like there's a transmit window size. What else controls the transmit window size? You just said it. You don't know you said it. But you just said it. Yeah, that's right. And what controls that? Yeah, but in TCP, what controls that? So you're right, and like I think you know what's going on. I'm trying to highlight that we have a name for it. It's called flow control. Right? The receiver advertises. There's in the TCP header. There's a advertised window field, right? Let's just look at the TCP header. Yeah. So if we look at the, there it is right there. This field, the advertised window field, is set by the receiver. And it's to tell the sender, this is the maximum window size I can accommodate. And the sender, if it conforms to TCP, is obligated to set its actual window size to be the minimum of this window and the congestion window. So if the congestion window is too large, and this is the constraint, then you cannot utilize the link. Right? When we talked about congestion control, I told you, usually the congestion window is the constraint. Right? The congestion window is the constraint that the receiver has to abide by, because this window size is often larger than the congestion window. And so when we talked about congestion control and rate, we just used congestion window and rate interchangeably. But that was with the caveat that that's the tighter constraint. But in this example here, in this example here, we saw that to utilize the 10 gigabit per second link, I need a very large window size. And this could be potentially larger than the advertised window that you were talking about. Yeah. Okay, good? Right? So with just this simple approximation for throughput, we can learn a lot. Right? It gives us intuition. It captures what I call first-order dynamics. Right? It allows us to provision, allows us to do lots of things. Right? It's going to be good enough for us. Right? It highlights, for example, the importance of RTT, right? And choosing routes and so on. So right now, for example, when we were doing routing, I told you there was a link, there was edge label. I just said, let's call it a cost. But actually, that edge label could have something to do with this. Could have something to do with latency, with round trip time. Right? It could have to do with dollar cost, but if you're interested in minimizing delay, it could be this. Okay? All right, are we good? So, nice little example, but it allows us to do a lot of thinking, let's say. Okay, what do I want to do next? Okay, so I think before we move on to this, maybe let me talk a little bit about, continue talking about TCP. For those of you just coming in, these notes are actually already in Canvas, okay? This is called TCP supplement. This is handout 11. This is TCP supplemental, right? So, okay, so if you remember, there were variants of TCP, and these variants of TCP generally differ in how they react to congestion signals, right? The two examples we saw were TCP Reno and TCP Tahoe, right? And yeah, so TCP Reno reacts to timeout in a very aggressive way, and triple duplicate acts by cutting the congestion window in half. TCP Tahoe reacts to both in an aggressive way by reducing it down to 1 and doing slow start, up to half the where the timeout happened or where the congestion happened. Okay, so assume that we have TCP Reno with slow start and AIMD. So now we're going to have AIMD. So here we're not going to look at the, let's say, average throughput. We want to look at the short-term dynamics. All right. So in slow start, let's say again. So I wrote slow start congestion window equals 2 MSS. This is a constraint I'm giving you. Right? I think when we talked about slow start, we said that, slow start starts at a congestion window of 1. But whatever, in this example, I'm telling you, slow start starts at 2 MSS. All right? So this is information that you're given. So slow start starts at a congestion window of 2 MSS. The current slow start threshold is 8. Okay? And let's say a timeout happens on the 5th transmission. And I want to know after the 10th transmission, what is the congestion window? All right, so for that we can just, we can just work through this. Right, so we're starting off at 2. Right, so that's what explains this. Hang on. That's what explains this 2. Now, in slow start, we have exponential increase, right? So 2, 4, 8, 16. But we know the slow start threshold is 8. So it will stop, right? So here, slow start will end because my slow start threshold was 8. And after slow start, we go into AIMD, which is linear increase in congestion window, right? So notice that, when I say transmission 1, 2, 3, this is after every RTT. Okay, so transmission 4 happens. So from here, the congestion window goes from 8 to 9 because we're in AIMD, right? And then timeout happens on the 5th transmission. So we go 9, 10. Then I get a timeout. Right now, at that time, because we're doing Reno. Right? Reno is going to cut the congestion window down to its lowest, and I told you that slow start happens at 2 MSS. So this will go 9, 10, then it will react aggressively, go to 2. Okay? And then after that, it will go back to slow start. Now, at this point, what is the slow start threshold? Because I had a timeout, right? So what's the slow start threshold? So based on this timeout, what will SS thresh be? Equals what? Sorry? Yeah, somebody said it? Yeah, so what is it? Why half of 8? At transmission 5, the congestion window is 10. That's when I got a timeout. Why would it be 8? Did you say 8? Who said 8? Why 8? But why are you cutting 8 to half, to 4? You said it's 4, right? No, so we don't keep a memory of this low start threshold. The network has changed, right? I told you a timeout happens on the 5th transmission. And the 5th transmission, the congestion window was what? What was the congestion window size on the 5th transmission? Yeah, so that's when it happened, right? So that's your new congestion boundary, right? So we understand what TCP is doing. It's adjusting the congestion window based on where congestion happens, when it happens. This happened at a congestion window of 10. Yeah? Yeah, it's 5. So we're going to, again, you could argue, why not 3/4? Why not 3/5? Yeah, there's no, half is not magic, okay? But TCP has it as half of the congestion window. So at this point, my slow start threshold is 5. Okay? So then, in the 6th transmission, my congestion window will go to 2. In the exponential increase 2, 4. Okay, so now what's going to happen? I mean, I've written something here, but we should go to 8, right? But the slow start threshold is 5. So what do we do? Is it 5? Is it 8? What is it? Well, what would you do? You're sitting there writing code, right? You are the network engineer who has to implement TCP. Yeah? Huh? Because I told you, slow start threshold starts at 2, at the very top. Right? Do you have the document open? Do you see it or not? If not, go open the document. Go to Canvas and open the document. Yeah, the very top. Yeah. So again, not to be confusing, but I'm giving you information. I'm telling you, I want slow start to start at 2. Yes, you're right. When we discussed slow start, I said, yeah, you should be aggressive and reduce it to 1. But now I'm giving you new information. So this is to teach you that it's not like anything is written in stone. Remember, I told you there are some things that need to be done because a decision needs to be made. Right? When you write a protocol, you have to be very precise. You have to make decisions on every decision. You can't leave anything to chance. But there's nothing that says you can't make different decisions. You could have changed the protocol. So what I did was I changed the protocol on you. Okay? So does that answer your question? Okay. So let's get back to transmission 8. In files, in handouts. You go to files, you go to part 2, and then handouts. Yeah, lecture notes. Lecture notes, sorry. And this is handout 11. Yeah, can everyone find it? If not, let me know now. What? Is it 8? Oh, sorry. Yeah, sorry. I changed it on you. I think it's, I'm opening up my local copy. At that time, it was 11. Yeah, apologies. It's handout 8, A08. You find it? Everyone find it? Thanks. Okay, it's in, yeah. So today we'll talk about this handout. We'll talk about routing supplemental and real world. Okay, that's the goal today. Okay, so we're still here. What's going to happen here? So I had a timeout at transmission 5. Set my slow start threshold to 5. My congestion window to 2, 2, 4. Then, what's going to happen now in transmission 8? What would you do? You are the network implementer. Sorry? Yeah, so that's what I did here, 5. But you realize that, again, there's no like decree from above that says you must do this, right? You could say, I'm going to go to 8 and then go to AIMD. There's nothing that says that you cannot do that, right? But yeah, I think a more reasonable thing to do is to stay within your threshold, right? So you're going to clip 2, 4, and then clip to 5. Okay, which is what I did here. Okay, then you go into AIMD, so 5, 6, 7. So the congestion window at the 10th transmission is 7. Okay, so yeah, I hope we now can appreciate the dynamics of at least the local dynamics, right? So global dynamics we saw we can estimate by essentially the standing rate, like W by RTT, happening locally. Well, here I went 2, 4, 5. So you, yeah, no, you go 2, 4, 6, right? Yeah. No, again, there's no you would go, right? It's your. Actually, honestly, I'm not sure. I think it does 2, 4, 6. But what I want to say is that there's not much. There's no real reason, strong reason for that. You could go 2, 4. That's being very conservative. 2, 4, 6 sounds reasonable. You go 2, 4, 8. That's being slightly less conservative. Yeah. Yeah. I know. You have to justify why you're right. So this is, I apologize if this is a bit of a shock to you, but in the real world, there's no black and white, right? You look in your own life, is everything black and white? Or is everything gray? Well, I mean, sometimes you know, as students in classes, we are taught everything is black and white, but it's not. Right? And especially because I want to train engineers who are going to go in the real world, meaning build new systems, not just fix old systems. You're going to build new systems. And when you build new systems, you're going to have to make your own decisions. So I want you to see the design space. There's a decision space where you'll have to choose. But yeah, I mean, to me, it's perfectly reasonable to stay within your threshold. So to me, it's reasonable to say 2, 4, 6. Yeah, I see where you're confused. Here I was thinking of going 2, 4 and going to 5, not stop at 4 and then go up by 1. It just. Yeah, you're right. So I think 2, 4, 6 would make sense. Yeah. All right, good. Are we okay? If there are any doubts about TCP, now's a good time. All right? Okay. So that was one last thing I wanted to talk about. I think, unfortunately, I printed this. Okay, so what we'll do is this. Maybe what we'll do is, okay, we'll just start here. Okay, so I want to talk about, now this idea comes up in TCP a little bit because it helps us understand how TCP is allocating resources. So I want to talk about the general problem of resource allocation, right? So again, it's not in the context of protocols or anything, but actually it's in the context of resource allocation protocols. And then in a real network, you would see there's a interplay between TCP and these kind of resource allocation protocols. Okay, but this is not specifically part of TCP, but it's a way for us to understand what TCP is doing. So let's say you have a router and you have 3 flows intersecting. I'll call these flows users intersecting at that router, and that router has outgoing link of 90 megabit per second, and these 3 users or flows are competing for that 90 megabit per second. Now, for the purposes of this setup, this framework, I'm going to assume that users request certain rates. They want certain rates. So user 1 wants 50 megabit per second, user 2 wants 50, user 3 wants 10. So this is the user requirement. And the question is, how do you split? Right? TCP does, it's a protocol for managing congestion, but at the end of the day, we'll see that TCP has to divide a resource, right? So that's why it allows us to look at TCP in a certain way. So let's talk about fair. Okay, I want to talk about fair alloc. So when we did, it was a similar problem, right? And we wanted to divide the bandwidth, and there we were looking at a certain perspective of flow identification. So here, assume I have flow identification. Okay, I want to now take my 90 megabit per second, and I want to divide it in a fair way. So let's talk about what are some notions of fairness. So that's the point of this. What are some notions of fairness? So can somebody help me? So let's say I want to divide this 90. I'll use this space up here, okay? Because it's a nice space, nice blank space. So so this is my setup here. Can somebody tell me what's one notion of fair? Like, what's the simplest notion of fair? Yeah, equal, right? So I can say, I'm going to do equal. So 30, 30, 30. Okay? So that's one notion of fair. Right? What's potential issue with this? So 30, 30, 30. What's a possible observation you have about this? It does look fair. Right? Everybody's getting 30. So, but what's a possible, like let's say this was your system, you own this router. Yeah. How are we wasting? Yeah, we see that user 3 only wants 10 megabit per second, right? And so when we do 30, 30, 30, we see this user 3 is not using all the bandwidth. So what's another notion of fair? Can someone else think of another notion of fair? Sorry? Okay, so proportional. What do you mean by that, Benita? Yeah. Right, so we see the total request is 110, right? And so we give everybody the associated fraction, right? So user 3 will get 10 over 110. So 10 over 110 of what, Benita? Yeah. And then these guys will get 50. Somebody want to compute this for me? What does this come out to? What is it? Whoever said it, be a bit louder. I can't hear. Is it? So it's 41, and what? That's 82. So that's 8. Is that right? Yeah, this looks more reasonable, maybe. Right? Because, well, I'm basing this based on what you are requesting. Right? So this also certainly looks fair. But what's the issue with this? What's a potential issue with this? Well, somebody said your issue still holds, right? That, oh, no, I'm not wasting bandwidth. Sorry. Yeah, I'm not. Correct. Okay. So there's no wastage. Okay, good. There's no wastage. But what's a potential issue with this? So this is not wasting bandwidth. Good. So what's a potential issue with proportional fair? Well, yeah, but so somebody's going to be unhappy, right? Because there's not 90 is less than 110, so somebody will be unhappy. But what's the issue with this? I'll give you it has to do with behavior. What? Yeah, that's what Benita said. But because 90 is less than 110, there's going to be unhappiness. I mean, we'll get to happiness in a second, but there's going to be unhappiness, right? So what's the issue with this? In terms of, let's say, the hint is, it's about behavior. Sorry? Yeah. Yeah. But that's what proportional fair is doing. So how does this, let's say, influence behavior? Yeah, exactly, right? The incentive here is to just make your requirement more. It's an arms race, right? Because I made it relative to what I request, I'm just gonna keep, increasing what I want. Even though, let's say, user 3 only needs 10, that's truth. It's going to request as much as the others. Yeah, so it's fair, but if you have, let's say, rational agents, it doesn't lead to maybe good behavior. If this was like an iterative game, it might lead to undesirable system outcomes. All right? So now we get to the happiness comments. So we saw that we don't want to waste. We also don't want to incentivize user behavior to be, let's say, greedy. So how can we do it? What's another way? So maybe the two people who talked about happiness can elaborate. Yeah, so we could maybe give user 3 10, and then take the remaining bandwidth and split it, right? So 40 and 40. This is what's called max-min fair. Okay? And the idea is that this doesn't incentivize anybody to ask for more than they want. Because you can ask for all you want, you're not going to get it. Right? So what this does is starts at the bottom and starts giving everybody. So the way you would do max-min fair is you would look at the lowest. The lowest is 10. You give everybody 10. Right? So actually, there are many algorithms. You can just guess max-min from here. But if you want an algorithm, you would start by doing like 10, 10, 10. Now you have 60 left, right? But user 3 is done, so you take user 3 out of the equation. You have 60 left, and you just take that 60 and you give it to the other two. And that's not going to meet their requirements, so you're done. So then it'll be 10, 40, 40. If for whatever reason, let's say that this was, let's say it was 60, 40, 10. So let's say that the request was 60, 40, 10. Right? Then max min fair would be 10, 10, 10. Then you have 60 left. Then what would you do? Oh, wait, in this case, in this case it wouldn't change, right? Yeah, in this case it wouldn't change. Let's change this to 30. Okay? Then what would happen? You would then leave this at 10, and you would give this guy 20 to make it 30. You would also give this 20 to make it 30. Wait. No, sorry. Yeah, 20, correct. So 20, 20. So that's now 40 gone. So there's 20 left. Right? And then you would just give that. Okay, so this would be the max-min fair. So it's essentially, in communications or in, it's a strategy called water filling. Okay, you basically start at the bottom, and you just start filling everyone until some users are full, and once you're full, you stop and you keep filling the others. Okay? And what this does is this, the most important thing this does is this doesn't incentivize users to ask for more than they want. Okay? And TCP is max-min fair. Now, if many times, like for example, in this case, if everybody was requesting 60, right, then max-min fair is just equal. So a lot of times, max-min fair reduces to equal rate allocation or equal resource allocation. Okay? And many times, that's exactly what TCP does. Assuming that flows have a lot of data to send, right? Typically, the amount they want to send is more than the link bandwidths. So you end up getting equal rate allocation. But the nice thing is that when that's not the case, TCP reverts to max-min fair. Okay? So the whole point of going through this exercise, and I think that's all I did here, okay, is the following. So actually, I wrote this here. This is actually wrong. Sorry. Okay, so TCP is actually max-min fair. And sometimes that's equal rate. Okay, so but my point in all of this is actually a larger point. All three notions that we came up with are all fair. So what matters is your metric for fairness. If you don't have a metric for fairness, you can't say what's fair. If you don't have a metric for goodness, you can't tell me what's good. So one way that people, one mistake that many people make is you might ask them, what's the best algorithm? And they'll give you an answer. But actually, you shouldn't be able to give an answer because you don't have a metric. You don't have a way to judge. If you give an answer, it means you're making an implicit assumption about what's good, right? You remember when we talked about layering, and I gave you the example of sending a letter. Do you remember that? And we had two ways of sending a letter. Use the postal system and fly to Hawaii. Right? Yeah, I still dream of Hawaii, right? So like if I ask you which is better, you might instinctively want to say the postal system is better, but you're making an implicit assumption that it's very expensive to fly to Hawaii. It's very expensive to take a flight. But what if your goal was latency, right? Then, or maybe was reliability. You know that, or it was privacy, right? You know that if you have the letter, no one else can read it. Whereas if it's in the postal system, there's a small chance somebody in the middle can open it, right? So you could have a different, let's say, metric that's important to you that could give you a different algorithm. So you should never be able to say what's fair, efficient, good, optimal, best. those are all meaningless until you give them meaning. Okay, so never make assumptions. Because for all you know, the next level, the next network, next system you design, the next generation internet may have different, different constraints. For example, now with tools like these large language models, suddenly things like false information and reliability is very important. And maybe the network needs to take that into account more than it does now. Right now, we're worried about cost, throughput, latency. But maybe the next level will have something completely different. The network will be so stable and so connected that latency is not an issue. Something else becomes an issue, and the algorithms will have to take that into account. So that's why I want you to open your mind. And that's the point of talking about this. All right, so I think that's all I want to say about TCP and rate allocation and resource allocation. Any questions? Okay. Okay, so I think that was... Okay, the second thing I want to do is there's a routing supplemental. And I think that one, maybe I'll go to Canvas, it's that one is A10. Okay, the routing supplemental handout. Okay, and here I just want to, so this is about network layer, and I want to close the loop on some things that we already talked about. But again, there were some questions, so maybe it's good for me to review some of it. So you remember that when we talked about distance vector, we had this issue of bad news travels slowly. So when link costs go up, it takes the network, let's say, a long time to eventually converge and learn about that change. So there's an example here. So here's a 4-node network, A, B, C, D. And I'm going to show you that potentially the amount of time can be infinite. The example I gave you in class, it took, remember, 44, the cost went from 4 to 60. And it took 44 iterations for the network to converge. Well, in this example, we'll see the network never converges. Okay? So let's say that in this example here, let's say that link CD breaks. Okay? So CD goes from 1 to infinity. Sorry, I'm having some allergies. Okay. Okay. So link CD breaks. Now, for example, so what will happen when link CD breaks? So you think pre-change and post-change. So pre-change, right? A, B, C will all have a route to D. But that route will go through what? You have to go through C. C is the only node that connects to D. So A and B and C all route through C to get to D. Now, when link CD breaks, only node C notices it. A and B don't notice it because they're not neighbors of D, right? So post-change, what will happen? I mean, you can read this, but it's better you think about it yourself. Maybe I should get rid of this because I think people have a tendency to read, right? Can I just... Fill it? Yes. Okay. Excellent. All right. So, I mean, you can get it, but there's a human tendency to just read. It's not like I don't want to give you the answer, but humans just tend to read. And I want you to think. Okay, so node CD breaks. A and B don't see that. Well, C will see that. But pre-change, what does C know? Pre-change, distance vector has converged. So what happens? What will C know before the change, like after convergence. Yeah. So C will know that A has a route to D and B has a route to D. Okay? And what will it do? It will try to use that route. Right? So now, so C will, now in this case, since A has a shorter route to D, C will play with A. It's not going to mess with B because that neighbor has a longer route. Okay, so it will say that, okay, I have a route 1 cost to A, right? So whatever cost A has to D, I can just piggyback onto that. And it will then update its cost to A. And what will it do? It will tell its neighbor. And more specifically, it will tell A. A will say, hey, oh, my friend C has increased its cost to D, and I want to use C. Because my cost to, because B's cost to D is higher, so I'm going to use C. And it's going to update its cost, and so on. And they will ping pong back and forth forever. Do we see that? Because there's no actual route to D. In the example in class, there was an actual route to the, once one of the things went up, or even if that link had broken, that 4 had broken, gone to infinity, there's an alternate route. Okay? Here, there's no alternate route. So nodes A and C will ping pong back and forth forever. I mean, B will also get messed up, but we're only looking at what happens right now between A and C. Okay, so this is the core problem. Now, in this example, will Poisson reverse fix it? Because Poisson reverse says, A is using C, right? So C will lie to A, right? So this fixes it here, right? Is it as simple as that? You shook your head, yes, no. I can't tell if you're like, which one is it, yes or no? Will this fix things? Why not? Yeah, exactly. A will say, oh, my route to D through C's cost to D is infinite. Right? No, hang on. Yeah, because, well, so A is going to use, A is going to use C to get to D. So A will lie to C. Right? But C says, I have another neighbor B, so I can use B. Now, B is not going to lie to C. Why? Because B is not using C. B is using A to get to D. So, B will tell C, I have a route to D. C will say, oh, my friend B has a route to D. And they will try to use it. And Poisson reverse C will then lie to B. But B is not using C. B is using A. And A is not using B. B will lie to A. But A is not using B, right? A is using C. So you end up in a perfect storm. Right? Everybody's using the other node that is not being lied to, that is not lying to, and we're going to get to the same problem. So Poisson reverse doesn't fix it. Okay? So everybody see that? I promise you an example where an example where you get the count to infinity and where Poisson reverse doesn't fix the problem. So this is it, okay? Okay, I think I didn't write here about the Poisson reverse. This is just a routing loop. Okay, this is, in fact, it's called a routing loop because like without Poisson reverse, A and C will just ping pong back and forth forever. But even with Poisson reverse, you still get a routing loop. It's a bit more complicated, but it's there. Okay, everybody good? So do you understand the potential issue with distance vector? Okay, this is it. Poisson reverse doesn't fix it, and the only thing that fixes it. What did I do here? Okay, I did talk about Poisson reverse. So Poisson reverse, doesn't solve the routing loop. Okay, good. Okay, so these two shows that in this simple example, not doing anything and Poisson reverse both lead, and using Poisson reverse lead to a routing loop. The only thing that will fix it is I think last time we said we need to know the path. So you have to advertise the path. In addition to sharing distance vectors, you share the path. Okay, and so this actually I took the statement from BGP. Okay, remember BGP was the distance vector based protocol used between autonomous systems, right? And so essentially a node is going to scan the full autonomous system path and check that the AS number of the local system does not appear in the AS path. So when I choose routes, right, choose the next node, I'm going to make sure to choose someone that I'm not in that path. Okay, and this is, did I write here? It's called the path vector. I mean, some people call it the path vector protocol. Okay, so it's an augmentation of distance vector. Okay, are we good? All right, great. Okay, then the last thing, I think this is my last slide on this is Dijkstra and negative edges. And this is vanilla Dijkstra, the original Dijkstra, and negative edges. Okay, so let's. I mean, this is there. If you don't mind, try not to read it. Don't make me black it out. Let's just go through nodes. We'll start up there, in that network here. Here. Let's start with that. Maybe, let me try, discard that. Let's go to A, okay? So in network A, will Dijkstra work or not? I think I'm going to have to. There. I don't trust you guys. No, it's not that. It's just human nature. Will Dijkstra work here? So I have negative edges, right? So what will happen here? Yeah, so what will Dijkstra do? Well, Dijkstra is going to take the greedy decision, so it's going to do that, right? And then it's going to do that, right? This is the output of Dijkstra. And is this the shortest path spanning tree? Yeah, it is, right? So the point is, the Dijkstra will work here. But does anybody see a principle? Why does Dijkstra work here? What's the principle? So this, maybe, yeah. 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 That's a good point. But yeah. So we'll come back to that. So I'm asking the question in network A, why will Dijkstra? It seems to work. Can you explain why it works? And give me a principle. Yeah. So that's kind of proof that it works. But can we derive a principle from this? So this points to a situation with negative edges where you can be confident Dijkstra will work? Can you identify what that condition is? Well, we saw that even though there are no negative cycles, Dijkstra may not work. And we'll see example of that. So that's not it. Okay, so let's hold that thought. Let's come to network B. We'll come back to A in a second. Let's go to network B. In network B, there's no negative cycle, right? Because there's no cycle. These are all directed graphs, right? Right? These were directed graphs. You can see that there's no negative cycle. So you tell me, what's your name? Wanjun? Yeah, Wanjun. In network B, will Dijkstra work? What will Dijkstra do? Yep, it will take AC, and then what will Dijkstra do on step 2? Okay. And is this the correct shortest path spanning tree? Yes or no? No. So is this the correct shortest path spanning tree or not? No, just speak up. I think people cannot see you. Just say yes or no. Yeah, it's not. So what is the shortest path spanning tree? What two edges are in the shortest path spanning tree? That's right. So now you've answered your own question. This thing has no loop, and yet Dijkstra does not work. Right? So no loop, and Dijkstra does not work. So I think Max, you were also saying the problem was loops, right? So it's not.
I thought it was undirected.
Yeah, okay, but let's say in this case, yeah. Okay, so now, what's the principle in A? Did anyone figure it out? Well, the negative edges are incident at the source. Right? So they're visible to the source. So being greedy doesn't hurt you. Right? So yeah, that's all it is. So if the negative edges are incident at the source, then Dijkstra will work, obviously, because it can see them on the very first iteration. Yeah. Yeah. You're saying if BC is 1, then what do you get? -4. Yeah, I mean, it will take it. Yeah. Yeah, it will do it. Yeah. So whenever, so the point is that being greedy doesn't hurt you because you've taken into account all the information. Being greedy hurts you in network B because you made a decision without seeing the negative edge. In A, you're making decisions by, and you've seen all the negative edges. So if all your negative edges are incident on the source. So that's the difference between A and B. Okay? Now Max, you mentioned something about loops, right? And so you could go around in a loop forever. That's potentially true, but Dijkstra will not do that. Right? Why? Can you tell me why Dijkstra will not do that? Yeah. Right, exactly. Dijkstra will terminate. Dijkstra will not terminate. It will terminate in at most n steps, if you have n nodes. The more important thing about having a negative cycle is that the question of shortest path doesn't make sense. So if you see a negative cycle, you should not be able to answer what's the shortest path. Negative, there is no shortest path. Or even saying there is no shortest path is maybe a bit dangerous. The question doesn't make sense. You shouldn't ask the question in a graph with negative cycles. Okay? Right? Okay, are we good? So let's look at the one on top. Okay, so let's do the same thing. What is Dijkstra going to do? Let's make Dijkstra purple. Okay, so Dijkstra was purple here. Dijkstra was this and this. And then, Benita, you had an example. You had A, B, and C, and you wanted to do this, right? So in this case, what would the first step be? It would be this, right? And the second step would be this. Yeah, okay, so the shortest path and Dijkstra are the same. Okay, so how about here? What will happen in network C here? What's the first step? Yeah, so the first step would be this. And then AD, BD, right? And then after that, this. So is this correct or not? What's the true shortest path spanning tree? Should be that. Then this, right? These two are in there because there are no other routes. But you should actually do this, right? So again, this is almost the same problem as B, right? You're making a greedy decision without seeing, yeah? So how about in network D? So in network D, the shortest path spanning tree is Dijkstra will choose this. Then I have a choice right now. Yeah, I can flip a coin. If I happen to choose this, then that's what I get. But what if I happen to choose that, and then I choose that? Because remember, ABD and AC have the same cost. So now, I'm going to choose that. So it turns out in this case, Dijkstra may or may not give you the right answer. It comes down to how you break the tie. Okay? Okay, and so the point is that if you have to break the tie with a coin flip, then too bad, right? But sometimes you are given, let's say, there are some policies for breaking ties. So for example, in this case, one policy for breaking a tie could be you should choose nodes, like when you want to break a tie, choose nodes that are closer to the source. Now, obviously that closer cannot be in terms of distance because there's a tie. So it's going to be in terms of, let's say, hop count. Right? So in that case, to break the tie between B and C, D and C, what would you choose? If I told you break the tie by choosing the node closer to the source, then you would choose C, right? Yeah. But again, that's not it just happens that in that case, this gives you the right answer. But it's not always going to. I could make it so that gives you the wrong answer, right? Okay? Okay, I think so. That's all I want to say. Is that negative, I just screw things up. Okay? But along the way, I think we learned a lot about Dijkstra. So hopefully, that was the whole point of all of this. It's that journey, right? That talking about the different aspects of routing, the algorithms for routing, and so on. Okay? Any questions? Okay. Let's do one more thing. Oh, by the way, I've also, in assessments, I've put up the solutions for 1 and 2. I think homework 3 is due when? It's due this Wednesday, right? Yeah. If there are any questions on it, now is a good time to ask. Okay? But on Wednesday, I'll upload the solutions to homework 3. Okay? But I've also uploaded a set of sample questions, sort of 27 questions. Okay, just made up some questions. I'm not going to assign. I was thinking about assigning this today, but I'll probably assign it on Wednesday. But I want you to actually work on these problems, and then upload your answers to Canvas. Okay? Yeah. The point is, if you do these, you're going to do much better on the quiz, better on the final. All right. So don't be. It's not that I want to add more work. These are very easy questions. They're to get you thinking, right? Like if you look at them, like the first 10, 15 questions are just multiple choice. It's just to get you thinking, get your juices flowing. Okay, then there's some questions here. I realized that some of them are related to what some of the questions I've asked you to solve in class and so on. Okay, so you can take and the point is in the assignment, you'll just have to upload either a text file or I'll give you a text box and you can just enter it there. But you can actually, if you want, you can start working on this now. But I'm not going to assign this today. What I'm going to do today is we're going to talk about yeah. The quiz is it's not this week, it's the following week. What's your question? It's going to be in this room. Yeah, I got to figure out. There's like, I think we should be able to get where was it? Is there a reason? Was it during the class time? But it was in a different room. I think there's too many people. Was LT11? Was that a big room? Yeah, I don't even think here we'll be able to get one seat between, right? I think everything might be filled. Yeah, even with one seat between, right? Cannot, right? Okay, I'm very happy that you pointed that out to me. I will try to arrange something. Yeah, otherwise, what we'll have to, I don't know. We'll see. Yeah. Okay, thank you, Benita. Okay, so what I want to do now is, okay, so in the class right now, we've learned a bit about theory. We did a bit of networking a bit with like ping, traceroute, Wireshark. So got a little bit, some tools to get your hands dirty. I want to now give you an example of how some of the theory that we learned, how it can be used to understand what happens in the real world. Okay, so that's, and maybe if I can remember that there's another story that is probably not here, but I'll tell you. Okay, I like cartoons. So this is actually one of my favorite cartoons. This is from the New Yorker magazine. It's a example of this. There's this older dog in front of a computer telling a younger dog on the internet, nobody knows you're a dog. And I like this article because it's actually the root of the example I'm going to give you, right? And that root is origin authentication, right? When somebody says that they're a dog, how do you know that they're a dog? Or if they say they're not a dog, how do you know that they're not a dog? Okay, and the example is going to be about Pakistan Telecom and how that ISP, along with the Hong Kong ISP, they work together to unintentionally take down YouTube. Okay, so it comes down to what I call weakness in internet routing, and that weakness is origin authentication. Right? Right now, I can know that a packet came from an IP address. So let's say I know that. But I don't know who that person is. I don't know who owns that IP address. Right? And what that allows nodes to do, like this has been patched by policy, but it's not necessarily patched in the core protocols. because the protocols don't have authentication in there, like the routing protocols. But policy on top of it has now fixed it. But this actually happened. So this lack of origin authentication can allow nodes to masquerade as other nodes. Now you might think that's a bad idea, but actually, when you think about it, I'll convince you that allowing that to happen is reasonable. Okay, and from a political point of view, it's required. Okay, so you still need mechanisms in place to make sure that this doesn't affect the entire internet. Okay, so what happened is this. Okay, so this is YouTube. I think I took this screenshot many years ago. So I don't know if YouTube is this space anymore, but let's assume that YouTube is 208.65.152.0/22. So what does this mean? So we should know what this means, right? This is the YouTube space. So what does that mean? That I told you that YouTube is operating in this space. Yeah, if you had to explain this to someone, like how would you do it? Yeah, can somebody volunteer, or I'll have to like pick people. Yeah, the guy in the back. Hi. Yes, talk to me. The first what? The 208 and 65. Oh, that's gonna record badly. Oh, sorry. Yeah, go on. But okay. Somebody want to clarify? What's your name? Spell it for me. A-N? Anurag. Anyone want to add on to Anurag or clarify what Anurag said? Okay. Yeah. 208 is a country code, you think? Okay. 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 Anyone else? What's your name? Ure. Okay, Anurag and Ure. Okay, we're getting. If I combine the two of you, I'm getting somewhere. Anyone else want to clarify? Okay, so good. So this is one observation. This last 22 means something, Anurag, right? What does it mean? Huh? Mm-hmm. Okay, you said it a couple of times. I was hoping we'd get it clarified. You're mixing up host and subnet. The first 22 bits are the subnet ID, not the host ID. They're the subnet part. And are you ready? Like country code comes into play and so on, but it's just the first 22 bits represent the subnet. That's what this means. So the first 22 bits, 208.65, that's 16, plus 6 more bits out of 152. Those 22 bits are the subnet ID for YouTube. So is everybody clear? So how many hosts does YouTube have on this subnet? Or can it have? How many hosts? No. I didn't hear you. Yeah, so it's 2 to the power 10 is addresses, and then if you want host, you subtract 2 because you don't want all zeros and all ones. Okay, so Anurag, are you with me? Are you sure? Yeah, are you ready? Are you okay? I think you all were on the right track, but let's be precise. Okay? Yeah, all this means is that the YouTube network ID is the first 22 bits, and that's what this is telling me. The /22 is telling me exactly that. Okay, so what this means is that nodes on the internet are advertising those 22 bits. Remember, forwarding tables store prefixes. The prefix is storing is these 22 bits. So every router on the internet, when it sees a destination that matches this, it will route it towards YouTube. Okay? Then, now what happened is, you guys might not remember this, but there was a time where there were these cartoons that were published, I think by some Dutch person or something, Danish. Okay, they published these cartoons. Some people found them blasphemous, and specifically, Pakistan wanted this blocked. So that's what I meant, that from a political point of view, they should be allowed to do that. They should be allowed to say, I don't want anything about these cartoons, any videos or anything about these cartoons. And in fact, they could just block YouTube. So that's what they wanted to do. They wanted to block YouTube. Okay, so what they did was, they told Pakistan Telecom, which was the main ISP, okay, to do this. So what Pakistan Telecom did was it advertised this prefix, 208.65.153/24. Now, why would this work? How would this block YouTube? Can anyone tell me? So you have to compare it to this. So what's the important thing here? What's the important number here? /22. What's the important number here? What is it? What's the important number here? /24. Why is that important? How do routers choose what interface to forward on? They do longest prefix matching. So /24, now assuming that the prefix is the same, right? And in this case it is. The /24 will match. So every router that sees this advertisement, okay, will send there. If I go to youtube.com, it will go to Pakistan Telecom. Because Pakistan Telecom is advertising this, right? They're saying, I am YouTube. This is the point. This is origin authentication problem, right? It's claiming to be YouTube, and you can't stop it. And you shouldn't be able to. The government should be allowed to do this. I mean, that's the point. So now, so all's good. You're in Pakistan. You go youtube.com. It tells you, sorry, you can't do this, or we're watching you, or something, right? Some scary thing like that. And this is fine. Pakistan Telecom gets its service, its ISP, its internet connection, from a Hong Kong ISP called PCCW. And the good thing is now we can start putting, I put up the AS numbers because we talked about autonomous systems, right? Yeah, so on the internet you can just identify people by their AS number. So PCCW is AS3491. This, so this advertisement will go to everybody, including AS3491. And that's no problem. It's on the network, right? It should get it. But what happened is PCCW made a mistake. They decided to forward that advertisement to its neighbors and so on. And then at some point, the internet had this advertisement. So that was really the problem. The problem is not Pakistan Telecom advertising this prefix. It was PCCW forwarding it. Okay? And that's it. And then YouTube was advertising this. What will happen? Think of longest prefix matching, and YouTube goes down. So this is, yeah, I can't remember where I got, there's a international body based in Europe that monitors AS, autonomous systems worldwide. And this is taken from them. This is YouTube availability. So you can see it went perfectly available. Then as the advertisement started to spread, it went down for some hours. And then it took a long time to come back. So how do you think it came back? Any ideas? How do you think YouTube got it back? Yeah, they had to hijack the route back. Exactly. So what did YouTube do? Okay, so again, yeah, so this is just showing you some of the timeline. So then what did it do so this happened at 1847. Around 2 hours later, YouTube decides to advertise its own /24 prefix. So did this solve the problem? No, right? Why? Because this is /24, so is this. Right? The reason it wanted to do a /24 is that it wants to cover as much of its space as possible. But the problem with having a /24 is that there's another prefix that's the same length. Now you're relying on the policy of the router. Who configured the router? It could be, their hope was that, well, maybe in addition to the longest prefix, time also played a role. So newer prefixes would be prioritized. But you can see that's not the case, right? That didn't happen all the time, right? Because you can see that it started to come back, but then not really. Okay? So it still took some time. Finally, they decided to advertise multiple /25 routes. And that fixed the problem. Okay, and then sometime later, PCCW also had to withdraw all of its prefix to stop the hijack. Yeah. And this is the entire timeline. So it took about 2-3 hours. But for YouTube, that's a lot of money that they lost. Yeah. Okay, and then, yeah, if you wanted to, in the notes, I've given you a bunch of links. You can go check it out. I think if you want to, we can actually look at, okay, so then there's just something on route hijacking. And the answer is no. In fact, you don't want to stop it. If you stop it, well, you can prevent a country from being autonomous. So what we need is better, maybe authentication, maybe better policies on when to forward these advertisements and so on. Okay? And then I think if you want to, I had a YouTube link here. Yeah, I think if you check out this YouTube link, what I found nice about this, it's an ad, right?
A good chunk of your time is actually spent writing emails. If you don't know what Grammarly is, it's basically a digital...
The RIPE NCC operates 14 route collectors worldwide. These collectors receive BGP updates from almost 300 peers.
Yeah, this is the company I was talking about, where they are monitoring worldwide, and they saw this hijack, and it's a really nice visualization.
Let us look at what the RIPE NCC Routing Information Service saw of the recent unauthorized route announcement affecting YouTube. This is BG Play, a tool developed by Roma Tre University in Italy in close cooperation with the RIPE NCC. The red circle at the bottom right represents Pakistan Telecom's autonomous system number 17557, and the red circle on the bottom left, the YouTube autonomous system 36561. On February 24th, at 1847 UTC, Pakistan Telecom started to originate a /24 covering address space assigned to YouTube. We can see that this route spread rapidly in the part of the internet observed by the RIPE NCC Routing Information Service. Within roughly a minute, the route is visible at most of the autonomous systems shown in this animation.
They said 1 minute, so it's very fast. Right? Things on the internet, the scale is very different.
And traffic starts to flow towards Pakistan. 17 minutes later, at 20:07, YouTube starts to announce the same route itself in order to route the traffic back to its own servers. Another 10 minutes later, around 2017 UTC, routing policy changes occur that move traffic for this route away from Pakistan Telecom's upstream PCCW AS3491.
Right here, this one.
Another 20 minutes later, Pakistan Telecom's autonomous system number is repeated in those routes announced by AS3491 in order to make them less preferable. Another 8 minutes later, the unauthorized announcements are no longer propagated, and both routing and traffic revert to YouTube at around 21:03 UTC. These animations and many other tools are publicly available at riz.ripe.net. There are also prototypes of new services.
Okay, so you can explore some of the, there's a whole bunch of stories written about it. Actually, this is not the route hijacking or these, what they call black hole routing. There are many instances of this. I think if you Google it, you can find many examples. But I thought this is a good way for us to understand, in the language of what we did in this class, a real event. The last thing I will tell you is this. It's a story that happened in this class. This was a previous version of this class. A student in the class, I think her name was like Maria or something like that. She came after the class and she told me this story, that she was working on campus somewhere with her friend, and Singapore's safe, right? So there's no crime at all whatsoever. So they just left their laptops and everything, and they went to go get some food. When they came back, their stuff was gone, right? Her laptop, her friend's project, some equipment and stuff, everything was gone. And they were very, very unhappy. But she remembered, because in class we do things like, if you remember, we were doing like looking at what your MAC address was. I would ask you what your MAC address was, get your IP address, and we were just talking about, she remembered this from class. And I think at that time, I'd also said that NUS does sometimes MAC address filtering, right? Like you remember we said sometimes that's how DHCP can hand out IP addresses based on your MAC address. So she decided to report she somehow had her MAC address from that exercise. I don't know why she had it written down or something. So she went and told Computer Center this. And Computer Center actually was able to track down her MAC address. So whoever stole her computer logged onto the NUS network. Yeah, and they were able to figure out which access point they logged onto, track it down, and she got her computer back. So I thought that was a cool outcome of something she learned from this class. Okay, so yeah, there's a lot of, let's say, practical things you can get from this class. Okay, thanks everyone. So any questions? I can stick around for a while. Otherwise, I'll see you on Wednesday. Thanks.